Yeah, we have the Devendra also here joined. Yeah, we can get started.
Hey, thanks everyone for joining on a Saturday afternoon. So this is the first time we are doing it on afternoon rather than we generally go at 11 a.m. ESTs. So myself, I'm Josna. I am the founder and the chair for ACM Richmond. And I have my folks over here who together we all contribute back to ACM Richmond chapter. So this chapter is more about learning, connecting, and innovating together, and also sharing your great research work or anything which you think audience would get benefited by getting that information. So today's topic is a bit closer to me because I am also into SRE and plus AI. So I'm super happy that Ravi is presenting Trustworthy AI in production because if we see, we all do super awesome during our POCs, but when it comes to production, it's entirely a different ballgame. So I am appreciative that Ravi is going to share his personal and also production level of insights in this session. Also, this event is special for one more reason because this is the first time we are collaborating with IEEE. So ACM and IEEE are going together so that we will have more visibility for the events and also more participation too. So without further delay, I mean, as I said, there is also an open position which we would talk at the end of the session. I will quickly hand it over to Rashid, who is the vice chair for ACM Richmond.
Hello, good afternoon, everyone. Thanks, Josna. Like Josna mentioned, so we are collaborating with IEEE. So this is our first session with that collaboration. We also have Devendra from IEEE. And I also want to thank Ravi for accepting the invite for the talk. Yeah, like just now saying the AI is everywhere in our lives right now, the development, production, maintenance, and everywhere. And this is one of the great topics that to understand how you are making changes in production, how to trust and how to push these changes to production, and such a wonderful topic. So I would really like to thank Ravi for accepting the invite and going to talk about this one. I'll hand over it to Khader and then Devendra for the quick introductions.
Yeah, thank you, Rashid. Yeah, hi guys, this is Khader. I'm the membership chair of ASM Richmond chapter. So my main responsibility is working on side of the members and so collaborating with the different societies in the local and planning for the future events and publishing that and coordinating to make it success and planning the future events. So that's the main my contribution here. And yes, so today, I mean, we definitely need to talk about. We have the Devendra. He is the secretary of the IEEE Computer Society Richmond chapter. So we recently collaborated, and we are looking forward to plan to do many more events together and to collaborate more on this event section. So, yep. Thank you, Justin. You can go ahead.
Yeah, we have Dipanjan. Dipanjan, are you there?
Yeah, I'm there. Yeah. Hello all. I'm Dipanjan. I'm the webmaster for ACM Richmond chapter. I just wanted to keep it short. So I just wanted to thank you, Speaker Ravi, for joining today and share his experience, and also welcome IEEE member today. Yep. Thank you.
Yeah,
Yeah.
I think.
Devendra, do you want to give a quick intro?
Yeah. Thank you, Joshna, for inviting us for this tech speaker session series. We are looking forward many more. Thank you once again. That's it.
Thank you, Devendra, for allowing us to collaborate. That's a great one. So we have some difficulties for our treasurer to join, but without further delay, I will turn it to Ravi for giving his awesome experience about the Trustworthy AI in production. Thank you, Ravi.
Get my screen.
Yes, we are able to see your slideshow.
Perfect. Yeah. So, yeah, hi, good afternoon, everyone. And thank you for inviting me to ACM and IEEE Richmond sessions. So this is Raviteja Reddy Mandara, and today I'll walk you through the Trustworthy AI in production. So we're building reliable, secure, and observable AI systems. So I want to frame this as a engineering workshop, not as a theoretical AI discussion. So in production, so the trust is not created by like saying that a model is accurate or by showing a single benchmark from the training time. So trust is created when a real system continues to behave correctly, when traffic changes, or when dependencies fail, or when the model changes. So and when the business asks like engineers to explain what happened during an incident. So the main message of the workshop is simple. Trustworthy AI is an operational property. It must be designed into the architecture, measured through telemetry, protected by security controls, and reviewed through incident evidence. So during this session, I will use the same language that SRE, security data, and AI teams can all understand. And I'll talk about reliability controls, security threat models, observability signals, and a short static demo report that shows what a production AI incident looks like when the data changes. So by then, my goal is that you leave with a practical operating model where you should be able to look at a system and ask like what evidence proves this system is reliable, secure, and observable. Let me start by setting the promise of this workshop. So we're not trying to cover every AI algorithm, every model architecture. So we are focusing on production operating model. The first promise is that we will define a trustworthy AI as an engineering property. That means trust is not only about model accuracy. Trust includes behavior under change, protection from issues, traceability. The second point is to that we will connect reliability, security, observability, and governance, and where many teams discuss these separately. So where data scientists can talk about accuracy, security teams can talk about prompt injection and data leakage. Third one is that we will practice the incident diagnosis. We will not only say monitor the model, we will ask what happens when production traffic shifts, like when feature freshness degrades, or when a support system starts making some unsafe tool calls. The final one is that you will leave with a 30 to 60 or 90-day implementation checklist, and that checklist is intentionally practical. It starts with owners, risk tiers, traces, and runbooks. So this topic matters now because AI has moved from experimentation to critical workflows. A few years ago, many AI systems were still pilots, notebooks, or recommendation experiments. Today, AI is appearing inside search, fraud detection, pricing, support routing, or customer service. So that changes the risk profile when AI is only an experiment. A bad answer is like inconvenient when AI is embedded into the prod, and one single bad decision can affect customers or revenue or compliance. So there are like three reasons this is especially important today. First, AI is becoming product infrastructure. It means like traditionally monitoring the AI is necessary, but using a CPU, memory, latency, error rate, all the monitoring which tells us like where the service is alive. They do not always tell us like whether the AI behavior is trustworthy. So when AI is so when I say production AI, that needs the same discipline and distributed systems. but it also needs AI-specific controls where it tracks the evaluation, drift detection, prompt, and tool telemetry safety checks. So for this workshop, I want to use a production definition of trustworthy AI, where trustworthy AI system is like reliable enough to depend on. Let us break that down. So reliability means the system works consistently under normal traffic, changing traffic or deployments. Reliability does not mean the model is perfect. It means the system has a predictable behavior, like or defined limits, safe fallbacks, and measurable quality signals. Secure means the system resists misuse and abuse. For a classic model, this that might involve data access controls, adversarial input handling, and model artifact protection. Observability means the system produces enough evidence to explain the behavior. Let's say if a user asks why a decision happened, or if an incident commander asks like why output quality changed, the team should be guessing like they should be able to inspect the input data, model version, and prompt version. And governance sits across all the three. And governance is how we decide a risk tier, ownership, and approval gates. So a practical way of to review any production AI system is like to ask like three questions. So can we trust it? Like, or can we protect it, or can we explain it? The first question, can we trust it, is about reliability and equality. So does the model behave consistently? Does it remain useful when input changes? Or do we monitor quality after release? Or do we have slice checks or calibration checks? The second question, can we protect it, is because it mainly because of about security and misuse. So can untrusted input override the instructions, or like are outputs validated before they are used by downstream systems? The third question is about observability, where the system produces a surprising output. Like, can we reconstruct what happened, or can we see the input prompt or model version, retrieval results, or tool calls? So these questions work because they are simple enough for leadership and concrete enough for engineers. If a system cannot be trusted or protected and explained, then it is not ready for a serious production use. So this is also a useful review structure for launch readiness. Before launch, like ask these three questions. During operation or measure these three questions. During incidents, investigate through these three questions. So the important point is on the slide is that production AI failures usually cross boundaries. The model is only one component of the risk surface. At the data layer, we can see schema changes, stale features, null inflation, distribution drift, or training serving skew or broken joins. So these problems may never appear as infra failures. The API is still up. The inputs no longer match what the model expects. At the model layer, we can see concept drift, calibration, decay, threshold errors, slice regressions, and all. At the security layer, we can see prompt injection, insecure output, sensitive data leakage, unsafe tool use, or excessive agency. At the system layer, we still have traditional reliability issues where latency, retries, fallbacks, or GPU pressure, or even cold starts. And finally, at the process layer, where failures happen when there is no owner or no rollback path, missing evaluations, weak change control, or no incident playbook. So the takeaway is clear. Do not debug only the model, debug the full production decision pipeline. So reference architecture. So it shows the production path from request to decision. So the goal is not to memorize every box. The goal is to understand where trust evidence must be captured. At the beginning, we have inputs in a classic ML system. Inputs may be featured from a future store, event stream, or transaction system. In an LLM system, inputs may include user prompts or uploading files, retrieved context, or sometimes even business metadata. So before the model sees the input, we need validation. where we check schema, freshness, permissions. These where many incidents can be detected early. If a feature is stale or if a required field is missing, sometimes even the system should know before the final answer is generated. So then we move through policy model or LM execution tools, telemetry action, and control plane. So the control plane is important because the production AI is not only about inference. It includes the model registry, prompt registry, or evaluation reports. Telemetry should be emitted throughout the path where we want metrics or for scales, for logs, for detailing the traces or the casual flows. This architecture is what allows teams to move from a vague complaint like the AI behaved badly to a precise explanation of like what changed and what action was taken. Reliability is built through controls that make change safe. In production AI, change happens constantly, like where data can change, users change, or prompt can change, thresholds can change. So the first reliability control is the data contracts, where the system should know if the required fields or valid ranges or expected categories and like schema limitations and all. The second one is canary release. Like for AI, canary is not only about service errors, it is all about comparing output quality, so score distributions and events and latency. The third one is fallback design, where like if the let's see if the mode is uncertain, or if retrieval fails, if latency crosses a threshold, or if a policy check fails. The fourth control is SLO discipline. So we need SLOs for latency and availability. The fifth control is registry discipline, where model version, training data lineage, or prompt version. The final control is incident trails. So if the team has like never practiced rollback or containment, the first trail incident will be a chaotic. So this thing is about making evaluation part of the release process. In traditional software, a build should not move forward if test fails. In production AI, a model prompt or a retrieval configuration or a tool policy should not move forward if the evidence pack is weak. The release flow starts with offline evaluations. These may include accuracy, calibration, regression, or test evaluations and all. Next, we run safety tests for an LLM application, where this may include prompt injection tests, sensitive data, policy violation tests, and unsafe action tests. So then we run slice checks where a model can improve average quality while hurting one important group or workflow. Slice checks helps catch localized regressions. A shadow run can let the new model or prompt observe production traffic without affecting users. It can sense a small real traffic under close monitoring. And finally, if the evidence is good, the change can move to production. So security starts with a simple realization where untrusted input can influence trusted actions. In a normal web application, we worry about input validation, authentication, authorization, and output encoding. In an AI application, natural language can affect instructions, retrieval, reasoning, and generated code and tool calls. So the prompt injection is one of the clearest examples where a user or a retrieved document can try to override the system instructions. The prompt may say ignore previous instructions or reveal the hidden policy or call this tool or summarize private data. So the danger is not only the text itself, the danger is that the model may treat the instruction as a legitimate context. So a common mistake is to think of guardrails as one major filter. So in production, guardrails are layered controls. So where they work best when they are distributed across the full path. At an input layer, we can see we can screen the prompts, scan upload files, classify and save requests, enforce rate limits, and block clearly malicious patterns. So this does not solve every problem, but it reduces obvious abuse before the request reaches the model. At the model layer, we use system prompt discipline, policy prompts, safety classifiers, or confidence rules. The model should know its rule, its boundaries, and when it must refuse or escalate. At the tool layer, we use arrow list, scope credentials, approved steps, sandboxing, and output validation. These where like least privilege becomes very important, and a support assistant may need to look up for the ticket status, or but most cases, but it should not automatically have permission to approve refunds or change account data. At the runtime layer, we use audit logs, anomaly detection, policy checks, human review, and incident escalation. So the layered controls matter because each layer catches a different class of failure. Input checks catch obvious misuse. Model controls that guide the behavior. The tool controls limit the blast radius. Runtime controls provide the detection and evidence. Together, they create a defense in depth for AI systems. Observability. Observability is the evidence layer for the trustworthy AI. A system may be reliable and secure by design, but without observability, the team cannot prove what happened. So for data, we monitor schema drift, freshness, and null rates. For the model, we monitor evaluation score, calibration, confidence, and distribution. For prompt LLM behavior, we monitor prompt template version, return context, tool calls, or token usage, refusal rate, or policy results. For system behavior, we monitor latency, error rate, throughput, saturation, retries. For security, we monitor injection attempts, policy violations, unusual tool calls, and suspicious retrieval access. For outcomes, we monitor feedback, labels, business KPIs or appeals, and customer complaints. The point is correlation. A good observability system lets us connect the data drift, model behavior, security event, latency, and outcomes into one incident story. So SRE teams already understand like SLOs, but AI systems need broader SLOs that uptime and latency alone. A system can be available and fast while still producing poor or unsafe, untrustworthy output. For reliability, we may track P95 latency or availability, fallback rate, or queue depth. For quality, we may track evaluation pass rate or hallucination or defect rate, grounded answer rate, or it's just not just like whether the API is alive. For data, we may track feature freshness, null rate, drift scores, and lineage completeness. So these signals tells us like where whether the model is receiving trustworthy inputs. For security, we may track prompt injection bypasses, sensitive data exposure events, unauthorization tool calls. For cost, we may track token budget per request, model routing efficiency, runaway loop detection, and cache hit rate. So operational thresholds make these signals actionable. If feature freshness exceeds like 10 minutes, alert. If prompt injection bypasses occur, block the release, or if P95 latency crosses the target, reduce the traffic or active fallback. So if evaluation pass rate drops, stop the rollout. So AI SLOs should answer the real production question like, is this the system still useful, safe, or explainable, and affordable for users? So AI incidents should be handled by with the same discipline as SR incidents, but the diagnosis dimensions are broader. The workflow on the slide is detect, triage, contain, diagnose, mitigate, and learn. Detection can come from many places. Drift alerts, quality regression, safety violation, security event, or latency spike. Triage asks, what kind of incident it is. Is it the data freshness or model regression or prompt change? Containment comes before perfect diagnosis. So if the system is producing unsafe answers, disable the risky tool, route to human review or lower traffic. We don't wait for perfect set. And diagnosis uses evidence like inspect the traces, prompt versions, model versions, deployment timelines, or output samples. Mitigation fixes the immediate issue and restore safe service. Learning turns the incident into stronger controls, like for better tests, better dashboards, and better runbooks. A strong postmortem should not say the model did something weird. It should show the input, context, version, trace, output, impact, and fix. So let us make this a practical. Imagine this is a scenario where a production AI assistant like suddenly gives unsafe refund guidance and calls the wrong internal tool on 8% of sessions. The service is up, latency may still look acceptable, but the behavior is risky and customer facing. So the first question is, what changed first? Was it the data, the prompt, the model, or the retrieval source? So this is exactly why we need traces and change history. Without evidence, every team will defend its own layer. The model team may blame the data team may blame the prompt, the platform team may blame the application. The second question is like which telemetry would prove the root cause within like 15 minutes. So I would want to see a prompt template version, model version, retrieved documents, tool call logs, policy checks, results, and all. I would also compare affected sessions with healthy sessions. The third question is, what is the safest immediate containment action? Like if the wrong internal tool is being called, or disable or restrict the tool first. If unsafe guidance is being generated, route those cases to human review or apply a stricter policy gate, then continue the diagnosis. The lesson is start with containment, then evidence. Do not debate theories like without traces. So now I'm going to So now I'm going to move from the slides into the demo report. So this demo is intentionally static and audience facing. So we want the audience to focus on the production pattern, not on the package installation or notebooks. So the demo is about like understanding like what trustworthy evidence looks like. And the scenario is like a production AI service. Let me share my Chrome tab. Yeah, so the scenario here is a like a production AI service. Like we have a baseline traffic, which represents normal healthy behavior. Then we have a shifted production traffic, which represents what happened after the environment changes. Maybe the upstream data pipeline, or maybe users started behaving differently. Maybe a feature became stale. Maybe security pressure increased. So as I open this report, I want you to look for 4 categories of evidence. So first is reliability evidence, where stale features, missing values, or latency increases. Second is data and model behavior evidence, like where drift and risk score changes. Third is a security evidence, where prompt injection or risky action signals. Fourth is operational evidence, where summary that helps the incident team decide what to do. So the first section is the incident summary. This is the executive view and incident commander view. Like we do not start with like 10 raw charts. We start with text that matter. So what changed? How big the change is, and what is the what it means operationally. So the first signal is missing device risk. In the baseline, this value is healthy, and in production, it increases. So that tells us like there may be a reliability problem upstream. Maybe the feature store is stale. Maybe a join failed. Maybe a new device type is not mapped. So the point is that the model may be receiving weaker evidence than before. And the next signal is uh, prompt injection or unsafe request pressure. If that increases, the system is not only facing a quality issue, it may be facing a security issue. This is why trustworthy AI connects security and observability. Then we look at the AI flagged rate or risk store behavior. If the model is suddenly like flagging far more sessions, or if the risk score shifts upward, that is a prediction behavior change. We may not have final labels yet, but we already know the system is behaving differently. So next we look at the P95 latency. If the latency, so latency moves from a healthy baseline to a higher production value, then infrastructure behavior may also be part of the incident. Now I move to the drift ranking. So this table ranks like which signal change the most. So this is useful because it prevents the random debugging. Instead of asking like what changed, we can ask which signal changed the most, and which owner should investigate the first. Finally, I look at the charts. So the chart makes the incident visible. The feature freshness shift, the risk score shifts, latency shifts, and the amount distribution shifts. So these are evidence like we would use to decide containment, rollback, retraining, policy tightening, or human escalation. So let us step back from the demo and summarize what it teaches. The first thing is that the silent failure becomes measurable when we collect the right signals. So without observability, the team might only hear that users are unhappy, or business metrics changed. So with observability, the team can see that feature freshness shifted, risk score moved, and latency increased, and the security pressure changed. So the second lesson is that the security becomes observable. In many organizations, AI security is discussed only before launch, but production security must be monitored continuously. If let's say if prompt injection attempts increases, or if risky tool requests appear, if policy violation rise, or if sensitive data exposure is detected, those should be operational signals, not just the complaints concerns. So the third lesson is that response becomes structured. So the demo does not end with the model is bad. It ends with an incident story, like production traffic no longer matches baseline, or some features are stale, shifted, latency increased, security signals are increased. So therefore, the response should be containment, data pipeline verification, permission review, rollback decision, and postmortem. So this is the difference between dashboards and operational evidence. So dashboard shows numbers, and operational evidence helps a team to act. So so that's the core message for this demo, where the trustworthy AI is not only about modern intelligence, It is about measurable behavior under production change. Now, let me move back to my PPT. So now we return from the demo to the LM observability, where LM systems add the traces because the execution path is more complex than a traditional classifier. So in a classic ML service, the input might be a feature vector, and the output might be a score in an so in an LM application, the path can include a user request, prompt template, retrieve context, or model call. So this way, the trace is part of the product evidence. So let's say if a customer asks like why the assistant gives a bad answer. So we need to know what prompt template was used, what documents were retrieved, what model and parameters were used, what tool was used, what policy checks ran, and how long each step took, and whether any fallbacks was triggered. So standard telemetry matters because teams increasingly use multiple models, vendors, frameworks, and agents. So without consistent telemetry, debugging becomes very hard. And with consistent traces, teams can inspect behavior, compare runs, detect regressions, and build stronger incident evidence. So governance becomes useful when it creates clear evidence, clear ownership, and clear action. Governance fail when it becomes paperwork disconnected from engineering. So the first governance practice is risk tiering. Not every AI system needs the same level of control. An internal summarizer has a different risk from a customer-facing financial assistant. So a read-only search helper has different risk from an agent that can execute business actions. The second practice is evidence pack. Before launch, the team should have evaluation results, threat model, test results, approval record, or owner list. The third practice is a runtime policy, where the system should define allowed models, allowed tools, acceleration triggers, and human approval requirements. The fourth practice is review cadence, where AI systems should be reviewed periodically because risk changes or data changes, model change, prompt change. So the good governance is not about like good governance like telling engineers like what to build, what to measure, who owns the risk, and what evidence to keep when someone asks like where the system can be trusted.
Ravi, just FYI, we'll be closing at 2:45 and opening the floor for questions. So
Yep.
if you can wrap up, that would be great.
Yep. Okay, so let me move to the key takeaways. The first one is trustworthy AI is an operational property, not a like a marketing phrase, like where a system is not trustworthy because a site says it's trustworthy. It's trustworthy when the team can show reliability evidence, security controls, observability signals. Second is reliability, security, and observability. Third is LLM systems that require traceability across prompts, context tools, policies. Fourth, the fastest path is measurable feedback, like where we keep, detect, explain, control, and learn. So keep the evidence, detect the change, explain the behavior, control the blast areas, and learn through postmortems and stronger gates. So if your team can do these things, then AI systems become easier to operate responsibly. They may still fail because all production systems fail. But when they fail, the team can respond with evidence instead of some random guesswork. Yeah, thank you again. Thank you all. Open for any questions.
Thank you, Anil. And thanks to you, first of all, Ravi. But Anil, I know we have stopped you multiple times, so please feel free to ask the questions now.
Sure. Yeah. Thanks, Josna. So first of all, hey, Ravi, this is really good presentation because today I think only 10% of the entire population who are using AI in the industry. Only 10% are succeeded taking it to the production. So obviously there are so many guardrails and open areas should be addressed. And I think your presentation is covering all of that in a very systematic way. So I have a couple of questions. If you could see the chat, I'll quickly go through that. So first of all, you mentioned about the consistency, right? So in programming world, we can maintain the consistency by having same input. It will go through the same logic, and we expect certain output out of that. But here, it is like very vague thing because we are giving the prompt, and then it is up to LLM model and agent to decide which way they will process that. And in that scenario, how do we maintain the same output or similar output? Is there any guardrails we should be putting in, or what is the guideline for that?
Yeah, obviously, so most of the teams, we continuously do like pilot testing where we have like the same kind of inputs where we get the expected output. But when we move our service to production, we can expect there are many changes from the either from the inputs or outputs. So definitely there should be guardrails at each and every level. So the first guardrail should be from the data, where we check the input data. That's where we expect the output from. And the next guardrail I strongly suggest is rollback path. So let's say if our LLM or if our agent is giving us like a wrong output or unexpected results, um, the rollback path should be straightforward to roll back to the previous release or to the previous original state to control the leakage. So it's like two things. The first one is to stop our LM to behave differently than expected. The second one is to roll back or move back to the previous state where we are, because we are in the production and we passed the test, and right now we are doing in the production. So
Sorry, are there any open source or paid tools actually which actually help us define these guardrails in a right way?
so for every, I think I'm not sure about third-party tools for the guardrails, but for any, I'm not sure if you use like a Codex or for any AI tool, when we are cutting a single PR, now we have a predefined guardrail section where we are creating all the guardrail steps and defining them, like what to expect and what not to expect. At least with Oracle, yeah, we are using at a PR level guardrails. So for every pull request, um, we are setting up guardrails and testing them in the production.
Yeah, I think the human in the loop factor will play a big role over here because as the systems get matured, until that time, the human in the loop will be helpful to review the output and ensure that it is up to the mark.
Yeah, that's a very good point. There was a discussion. So now we are seeing AI writing the code, and we are making AI to review the code. So we definitely need a human in the loop, uh, at least for the final approval or for at the review stage.
Yeah, when you are talking about production system, I think that is a must-have thing. But yeah,
Thanks. I'm done with my
Thanks for the question.
questions. Yeah.
Yeah. Any other questions for Ravi? Okay. If not, thank you, Ravi. Also, regarding the open position, which we spoke in the introduction, Rashid, if you want to throw some light on it to our audience to see if there is any interest where they can submit, etc.
Yeah, so like just I mentioned, we do have one open position for one of the officers. Yeah, if anyone is interested, or if you think you know someone who may be a right candidate for these officer roles, please let them know. And we have created a website, and yeah, it is a webmaster role. We also created a website to submit the intake form. Please feel free to submit, and we will do the review and evaluate, and then we can proceed further. I can share the website address here.
Rashid, what is webmaster role? Can you elaborate?
Yeah, I think Deep is the right person because he was our webmaster, and now he's moving to another role within the chapter.
Yeah, I can just tell something. So, like if I talk about like what actual very core responsibility, it is more about like to making sure like all the communication that is happening for this event or maintaining the website, okay, plus kind of doing the campaigning for the event. So all this kind of come under that webmaster, but it can be like more in the sense like in our ACM Richmond, like it is not we just focus on some specific task. We all share the work. We all share the work with each other. So, for example, I also try to create some poster for the ACM Richmond. So those are the core responsibility. But what I'm trying to say is not limited. Like he can always expand his work to more areas and can help others. It is like we all share the work.
Yeah, so yeah, like Deep said, yeah, so there are specific set of tasks for each officer role. In addition to that, we also take the load from each other and we distribute the work.
Got it. Thank you.
Yeah, if there is any problem during submission or anything you want to discuss, you can reach out to us at info@acmrichmond.org. That's our new email ID. You can reach out to us. One of us would definitely respond to you. Yeah, it may take some time because there are more number of emails these days, but we promise that we'll get back to you.
Yeah, also the website is still under development. It may take another 1 week to complete the full website with the latest content and everything. But yeah, so the joining us function works great if you want to apply through online. Yeah, and website should be ready in another week.
So this is Renu Lakla. I think Josna and Rasid and Kadravel, I met you guys during the IEEE meeting previously.
Yeah, thanks, Renu, for joining.
Yeah, no problem. So basically, I'm pretty new